Assalamu alaikum. My name is Mohammed. I'm from Software Engineering Group B, and today we'll be exploring graphs. This presentation will explore the fundamental concepts of graphs in data structures and algorithms. We'll delve into different representations, types, and traversal techniques, providing practical examples and applications. First of all, starting with what are graphs. Graphs are a fundamental data structure used to represent relationships between objects or entities. The key components of a graph are that they consist of nodes, also known as vertices, and edges. Edges are basically the connections between those nodes. Then let's talk about the representation of these graphs. There are two ways we can represent a graph. The first one being adjacency matrix, the second one adjacency list. First of all, we'll start with adjacency matrix. Here is a graph given to us. These nodes are basically the vertices, and we form a matrix which has the size of n cross n. Basically, n is equal to number of vertices, so the total number of vertices is what n represents. Here the total number of vertices are 1, 2, 3, 4 and 5. So the n is equal to 5. So we'll have a 5 cross 5 matrix over here. Then we'll check the graph if it has any loops. Any loops means if if an edge starts from a vertex and ends on the same vertex. Do we have any loops here? No, we don't have any loop here. So in that case, all the diagonal nodes will become 0 over here. So this will become 0, this will become 0, and this will become 0. After that, we'll check 1 for 2 and so forth. So this has a direct connection from 1 to 2. There is an edge connecting these two nodes, so this will become 1. Then we'll check 1 for 3. Does 1 and 3 have an edge connecting them? No, they don't, so this will become 0. Then we'll check 1 for 4. Does 1 and 4 have an edge connecting them? Yes, so this will also become 1. Does 1 and 5? No, so this will become 0. And so on. We'll do the same process for each one of them. After filling out all the values into the matrix, then this will be our result. So this is the way to represent this graph in adjacency matrix format. Then talking about the space complexity, that we'll get would be theta n square. Why n square? Because we have n number of rows and n number of columns, so the space complexity that we'll get would be theta n square. Now coming to a second representation of graphs, we have adjacency lists. We're going to use the same graph and represent it using this representation. In this representation, each node maintains a list of its adjacent nodes representing direct connections between them. So first of all, we have 1 here, so we'll connect it like this, and we'll have here we can see that 1 is directly connected with 2 and with 4, so we'll write 2 here. Then we'll check with 4, so we'll write 4 here as well. As you can see, does any other node have any direct connections with 1? No, so then we'll move downwards. Coming to 2 now, we can see that it has direct connections with 4, with 3 and with 1. So here we'll write 4, 3 and 1. So we'll continue the process for the rest of them as well. Now After filling out the rest, this is the result that we'll get. And this is how you represent this graph using adjacency list representation. Coming to the space complexity, the space complexity for this situation we have is theta n plus 2e. Now you might be wondering what 2e is. Basically 2e represents that each edge has been mentioned twice here. As you can tell, we have 4 with 1 and 1 with 4 over here. So we can see that each edge is represented twice uh, every time in this. So that's where we get the 2e from. And that is those are the two representations.